Hello everyone and welcome to another episode of Mechanical Warriors. My name's Josh Cav and today we're going to be talking about how to make your rotary do this. Yeah, let's do it! So how do we create that brap, brap, brap sound from a rotary engine that we all know and love? So this is similar to camming a motor. If you were to put a large cam inside of an engine, it will at idle run very, very rough. And this is because when you change the cam timing in an engine or you open the valves for longer or a longer duration, what you're doing is you're creating that valve that allows air into the engine. When it's open only partially, as the air is passing through, it's being sucked. And because it's being sucked, it creates a bit of a vacuum which causes the air to travel faster around it. So air travels through into the engine quicker under low RPM from a smaller valve, right? But if we increase that valve size and allow more air to flow, the air actually slows down. And this is why we lose power when we on our lower RPM, and we lose vacuum pressure on lower RPM when we increase our cam timing, is because of that reason. And a lot of variable cam timing systems like the Honda, I think it's called the Honda VTEC or V something anyway. But basically what it does is, as the engine is in lower RPM, it uses oil pressure to change the cam profile so that your valve timing is under lower RPM is opening at a shorter duration, which is basically decreasing that hole, which is increasing the velocity of the speed of the air traveling in, which actually makes more power under your lower RPM. And then as it goes up into your higher RPMs, the valve opens up wider, letting more air in, and it makes more power under your higher RPMs. Now with a rotary, because we don't have any cams or anything like that, the rotary timing is set in the actual housing itself, similar to how a two-stroke engine has a hole drilled into the sleeve of the piston, and that is our valve timing. As the piston comes down and that hole is exposed, air and fuel comes into the cylinder, comes up and compresses, and the rest you all know. A similar thing happens to a rotary. As the rotor passes the face of the valve will open, allowing air and fuel to come in, and then the combustion process happens. But to get that brapping sound, we essentially need to change the valve timing on the rotary so that our intake is opened longer, so to the point where our exhaust valve is just starting to open and our intake valve is just opening also. And this creates what's called overlap, is where our intake and exhaust valves are kind of partially connected for just a brief moment. But this brief moment creates a kind of a jump in air pressure in between the exhaust and the intake, which creates that bop, 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 bop sound. And it's kind of like a gas kind of farting up from the bottom exhaust up into the intake side of the combustion chamber. Basically what we need to do is change our valve timing, and the way we do that is by literally cutting the valve and reshaping that valve to a different shape, and that's how we change the valve timing. Now, this is done via traditionally using a bridge port, or you can also do what's called a semi-peripheral port, which is what I'm going to be doing on my next rotary build, simply because I like the idea of the air and fuel coming into the center of the apex seal instead of the sides, because it's just better if we're cooling from the center, and that cooling effect spreads across the apex seal from the center outwards. Anyway, changing the valve timing is one thing, but you also have to tune the engine correctly in order to get that brapping sound. So I'm going to show you, again, I'm not a professional tuner. This is just what I've done with my engine. It works for my engine. Every engine will be different depending on how you've cut your exhaust timing, your valve timing. So that will heavily depend on how the engine idles, where it starts brapping. If you've got a really big, massive bridge port or a huge peripheral port, then it's going to idle slightly higher than someone who's got a smaller bridge port. Then it will idle a lot lower in the RPMs to get that brapping sound. And you do have to find your RPM. Generally, with most bridge ports, it's around that 1700 RPM, but it can be up as much as 2200, but as low as 1500, depending on how you've set up the ports. So I'm going to dive into the Haltech software now and show you how I've tuned the car in the idle part of the tune in order to create that brapping sound. So let's get into it. Okay, we are connected to the car and ready to go. All right, so the first thing, let's go into idle control. All right, so idle control. Now, this is very important with the rotary. Now, there's two modes of idle control when you're using the Haltech system or other ECUs also offer closed and open loop modes. But the difference between a closed loop and an open loop mode in your idle control is basically just setting an idle value for a specific temperature. As the engine increases in temperature, you'll have a specific idle value, and that's it. It doesn't change. The problem with this is, let's just say the car's been idling there, and it might get a little bit of oil built up on the plugs or something like that. And as you're idling, it starts to decay away, and the idle might start dropping, and eventually the engine will die. Having an open loop system in your idle control, the engine will simply just die away. But however, with a closed loop system, if it goes to stall, the Haltech system will put the idle output up to 100% of its allowable amount, which we've set here. Our max position is 10%. So it'll put it to 10% in order to stop the car from stalling. And it will also it'll make minor adjustments to keep or maintain a specific targeted RPM idle across your temperature range. So I do recommend using the closed loop system if you can, especially under a drive-by-wire setup. You can also, if you're using a cable setup with your rotary, then most of the REW engines have a little solenoid in the intake manifold that you can use. It's used as a choke, but you can also use it as a stall saver. And you'd obviously wouldn't use this idle control function. You'd use your stall saver function inside engine functions and then stall saver. But we're not going to get into that. Now, a few things with the closed loop system that you need to know. With Haltech and with most ECUs, when you take your foot off the gas, the ECU goes into a zero demand section or a decel event. Now, normally with most cars, what they do is they cut the fuel in a decel event. Now, with a rotary, we don't want to do this because the oil that lubricates our apex seals is delivered from our fuel if we're pre-mixing the oil, which if you're not, you should be, because that's the most reliable, safest method to do it. If you've got an oil injection system on the engine, get rid of it, pre-mix the oil. That's the only way to go. So anyway, we don't want to cut the fuel in decel events. So we want to go to decel, and we've got decel cut, a switch here. We want to make sure this is off. Now, another thing too, in here, these events here, now this is a little bit confusing too. And basically, you want to have a number just above or just before your target idle, and this one just over your target idle across your temperature range, right? Now, I'm not going to get too much into this, but this is basically what triggers your decel event. Now, the reason why this is relevant is because when you are in closed loop mode, the engine, so it will say the vehicle's max speed before it goes back into closed loop mode. Now set this at, I've set this at 10 kilometers an hour. I was setting this higher, and I was having problems where the car was idling higher, and then as soon as I would hit 30 kilometers an hour, it would drop back down to its idle. And basically what was happening was the when when the engine is in decel mode, it goes from closed loop to open loop. Now, when it's in open loop, it uses this base map, right? So this here has to be set, and is one of the first things you need to set. Well, actually, the first thing we need to set is the target RPM. So we set our target RPM here, and then we start the car up and set our base map here. Now, what this is this is a percentage, 0 to 100% of our 10% allowable throttle position. So I'm saying I want maximum 10% of the throttle position in idle, and then across this temperature range, 87% of that 10% in all these different temperature ranges. At 30 degrees, I want it at 89% of that 10%. Okay. If I put 100% here, then it's literally going to take that whole 10%. All right. That's what these numbers represent. So what we want to do then is start the car up. Once we've got our target RPM and we've told it we only want 10% or 15%, whatever you want to put it, you can put in. I wouldn't put anything more than 15%. Set your target RPM, start the car, and then you need to go through as the temperature climbs, change these numbers till you get very, very close to that target RPM. Now, the engine, if it's bridge ported, will start brapping a bit, but it'll jump between brapping and sort of like a cavitation state where it's sort of going brap, 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 and I'll show you how to fix that so that it just sits there going brap, 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 brap. And the way we do that is two things. First of all, we need to go to our fuel, our target lambda, and just make sure that in our idle section, we're targeting an AFR reading between 13.5 and 13.8. Now, this will vary for different engines depending on port sizes and all that, but I would start around that area. You don't want to make the mixture too rich. They brap better on a leaner mixture, but you can't go too lean because you'll get glowing red hot exhausts. And this is because when fuel is being burnt, imagine a space, and inside that space you've got fuel particles. Now, if you've only got a few of them, then as the ignition happens and the fire is traveling from one side of that space to the other, it's got to burn and jump to all these different particles. And so it takes a while to get there. Now, what's happening when that combustion vent's happening, because it's taking longer because there's more space in between each particle, there's more heat being generated because the combustion vent takes longer. However, if we add more fuel, there's more fuel particles in that space, which means that the combustion can happen much faster. So it travels from one side to the other much faster, which means we actually create less heat. So more fuel creates less heat. Less fuel to a point creates more heat. So you have to be careful not to run it too lean because otherwise our EGTs, our exhaust gas temperatures, will go through the roof and we'll get glowing red hot exhaust while we're idling. So once we've got that set up and the car is running and you can see the target lambda and your actual AFR, so check your wideband O2 sensor and make sure that it's reading your target lambda AFR readings. If you're not using O2 correction control or some form of correction control, you'll have to manually go into your base map, change these values until you have that targeted AFR reading as your actual AFR. Once you're happy with that, if you want more information on this fuel tuning, check out my how to tune road tuner rotary. I go on into a little bit more detail with that in that video. Anyway, once we're set up our fuel map, the next thing we want to do is set up our ignition zero demand table. Now, what this does, I also talked about this in the road tuning episode, but I'm going to go on a little bit more detail about this. Now, zero demand basically means there is zero demand from the engine, means your foot is off the pedal, right? So when the foot is off the pedal, this map is now in play, and this is the timing map. This is saying at 1650 RPM, I want 19 degrees of timing. At 1800, I want -8. Now, why do I have -8 here? So I've targeted for my, let me just go to my idle control. My target RPM is 1760, right? Now, if I go in here at 1750, we've got 19 degrees of timing all the way up to 1750. Now, a positive timing like this or high degrees of timing is actually creating a little bit more power in the engine, which will cause the engine to want to accelerate, right? But as it accelerates into that 1800 RPM range, we've got a negative timing value, which is basically pulling power from the engine. So then it falls back and we have a backwards and forwards motion. Bop, 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 bop. Now, naturally, the engine will want to brap. You will hear it brapping occasionally, but it will be interrupted with this. I don't know what the word is, but it's kind of like a cavitation. That's the only way I can explain it. But the sound is when it's going blah blah blah. That state, sometimes it can get stuck in it for ages and it just sounds terrible. When we change the timing like this, it hits the 1800, it jumps back into 750, and if it does get in that cavitation state, it jumps out of it straight away and goes back into that nice clean rap idle. So again, this will vary depending on port sizes and whatnot, how far you want to retard the timing. So retarding the timing means putting it after top dead center, and advancing the timing is before top dead center. So anything with a negative number is happening after top dead center. Positive numbers is before top dead center. Now you don't want to go too far advancing the timing on idle because otherwise you will get a detonation event. Might not cause any damage, but the engine will eventually pop and stop. That is basically that. Now, these two different tables here, this off and on represents the aircon compressor output state. So when it's on, we can target a different degrees of timing from on to off. And the reason why is some compressors draw a lot of load against the engine. So what we can do is run a slightly higher timing to compensate for that load on the engine. And that way, when the compressor comes on, there's no change in the RPM idle at all, and you just keep getting that nice brap, 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 brap. However, I find if you keep these timing values identical across top and bottom, it should run perfectly. But if you don't, if there, you might, depending, like I said, every engine's different. So if it's not idling the way you want with the compressor on, with your aircon on, then just have a play with this timing. Now, that pretty much does it. I will finish up with this last bit. Make sure that when you're coming back down, so if you take your foot off the accelerator at, let's just say you've just done a massive pull and you just take your foot clean off the accelerator, you have to remember that when you take your foot off the accelerator, anything past 5,000 is going to be 25 degrees advanced timing, right? So if you have a negative number in here, all of a sudden you're going to have a heap of fuel being dumped, or basically a heap of fuel into the exhaust. And then all of a sudden the remaining fuel is going to be burnt in the exhaust because you're retarding the timing, and you'll get massive backfire events and popping and stuff like that, which you don't want to go too far in that. So keep a bit of advanced timing and then sort of taper it off to your negative point here. Now, if you're too high past this number and you have your idle target slightly too high, let's say we were targeting 1780, and you could be coming down in the RPM. So when you're take your foot off the accelerator, if it's up in here, you got to remember that timing is going to add power to the engine, which means if it's got enough fuel and it's got enough air, it will hold the RPM, so you won't actually decelerate. So you want to make sure that the engine is decelerating, and that is basically just a little bit of tinkering between your target RPM, your total maximum allowed throttle for idle, and these timing values across here. Now, feel free to copy this map here as a starting point for your own engine. I don't see that there will be any problems there, providing that you have your fuel target lambda set up correctly. It should be fine. And yeah, that pretty much does it for how to make your rotary brap. So, as always, if you guys have learned anything from this video, please consider liking and subscribing to the channel. That stuff really helps out. And as always, guys, enjoy the car scene. We'll see you next time.